Okay, thank you, Rodrigo. We are talking about Logmeter here, an automatic measurement system for forestry industry. So the next one, please. So Woodtech is a Chilean technology development company. So we are a team diverse and innovator. We like to work closely with our clients, understand their needs and on the field, and respond with value-added solution to the process. We design, develop, and implement solutions censoring the real world, making it possible for our clients to access accurate information on their processes. We are present in many countries, United States, Chile, Brazil, Uruguay, Germany, Australia, and the main pulp good producer in the region trust in our solutions. The next ones. So we make visible the invisible in the forestry process. Our offer is made up of automatic system by means of the capture and sensory of the real world, deliver relevant information online in order to allow our clients to make informed decisions for their processes. The next one. Now we are talking about Logmeter. Logmeter is an automatic system that delivers in real time high precision volume measurements and estimate biometric characteristics of good logs loaded in a truck. The next one, please. Here we have a skin of Logmeter. First, we have the starting process. The start of the process can be with our RFID or web service. Then we start the capture process. We estimate first we estimate the speed of the truck. We have two laser to estimate the speed of the truck, and 7 or 11 other lasers to estimate the load profile. And also we in this step we import data from our client. For example, invoice ID invoice or species of the logs, etc. And then we have the segmentation process to separate relevant information. And finally, we have the calculate model and then the deliver results. The most important variables in the pulp industry are the solid volume, the volume of log. In this sense, our first approximation to that is the volume that surrounds the good. We have different kind of the definition of this volume. The first one, no, you don't see my mouse, no? That's, thank you. The second box, red box, please. The first definition of volume is the stereo volume. It's the bounding box of the logs loaded. This is the that kind of stereo volume. The volume, sorry, is the typical procedure used by manual procedure. The second one is the delivered by the Logmeter. It's the stereo volume, reduce the peripheral error. In order to reduce the peripheral error, and then as we can see, the stereo volume measurement includes error between logs. So then with a modeling processes and employing the biometric automatic characteristic and also the stereo volume, the Logmeter delivery, that Logmeter delivery, we try to predict the solid volume presenting the log file. Second, next, please. The solid volume estimation is a typical supervised machine learning based procedure. We have a training data set with a reference, with a ground truth. In this case, the solid volume is the objective variable. And then we have a step to analyze the biometric variables to select the more correlated variable with the objective variable. And finally, we characterize the predict model using cross-validation methodology. And also, we have a testing data set to evaluate the predicted model. The next one. This experience that we are presenting here use a ground truth based on Archimedes principle or Archimedes formula. Archimedes formulas is commonly used in the region, but in a different way or quite different. Typically, the typical Archimedes based methodology take a sample of log pile and then estimate the density, and the density is applied to the whole volume, logs pile. In this case, when we use as a reference of Logmeter, we estimate the whole volume. So we take the logs from the pile, as many as necessary to immerse the whole pile. So the volume of the logs is the sum of volume estimated with the Archimedes formula. The next one. So here we have the Archimedes formula, the main formula, and some statistic from the process. For example, 4 grapples in average for a typical bundle of logs. And we can see the density variation in a same group of logs pile. And we can see variation between 3% and to 5%. So estimate the volume of pile as a sum of volume and take the whole pile is very important to us. And in order to use this volume as a reference. The next one. So it's important to mention that our unit sample is the pilot good. We define this pilot as a bundle. We can see the red box here. That is the bundle. It is our unit sample. So we have 5 predicted models. Each model represents a specific type or a specific class of pilot wood, species, type of length, etc. The capture or the sensory presence follows a very important relativity control, obviously considering the product terms. And also we measure and control the precision of all automatic variables, automatic biometric variables that deliver the Logmeter. The next. So we have the predicted model results. We use leave one out as a cross-validation methodology because we don't have many or great volume of data. So leave one out is more, it's better, you know, it's better. So we can see the standard deviation of 5 models is limited to 6%, and the confidence interval at 95% level less than 12%. It's important mention that regulation for pulp good in Scandinavian countries limits the standard deviation at 9%. This standard is not used in just in Scandinavian countries. It is also used in other countries of Europe. So it's very important to keep in mind this value. So we remark in the graph by the red line, Second one, and the next one, please. In testing results show similar performance to that found in cross-validation process. The average difference compared with this ground truth with the Archimedes-based reference are less than 2%. And when we talk at track level, log track in this client is composed in average with two bundle of logs. When we talk at track level, the standard deviation limit is reduced to 4% compared with the Archimedes reference. The next one, please. So here we have the precision of the main volume that delivered the Logmeter, and here we have 20 track, yes, 20 tracks, 10 repetitions per track, and we can see that the precision is limited to 2%. The next one, please. So, as mentioned before, the Archimedes process is a common practice in forestry industry. Therefore, achieve successful results with this methodology with our predicted models. It's very important for us. So it's a very important conclusion for us. We have a confidence interval limited to or bounded in 12%. So it's a very important results. And we keep the precision limited to 2% and automaticity greater than 98%. So it's a very important result and without or few manual assist. The next one, Marie will be present.
Thanks, Carlos. Yes, I will talking about another component of Logmeter, which is based on computer vision, and also it gets a result in real time. Currently, our traditional Logmeter is based on so many lasers, which makes the system really expensive for some part of the forestry industry. So we have been looking for a system which can be less expensive, but also to get another results, like counting of logs, and maybe to give one dimension of the logs, for example, radius. So we started with computer vision system, and in this case, it is really similar to the Logmeter flow, but it changes obviously the capture stage. So we take images from the track, from the back of the track for each bundle, and then we make a segmentation of the logs in the image in order to detect how many logs we can observe. Then with the detection of each frame, we choose the best one. The best one detection is the number of logs that the bundle has. And next, the information is reported to the client, and it can be fixed if a problem or maybe 1 or 2 logs weren't correctly detected. So let's check how it works in detail. So at the start, we were working parallelly in a segmentation process and also on a stereo vision system. So we made a pilot installation with 2 stereo cameras at both sides of the road where we had a traditional Logmeter installed. So each pair of cameras can capture one side of the track. We had to look for an angle that could capture the most part of the back of the track in order to detect all the logs, or at least more of them. Well, we used a deep learning technique to detect the logs, and also we defined 3 kinds of classes. So the first class was full logs. So it means we can see all the geometry of the log, a circle or ellipse. It was the first class. The second one was logs that are covered by another log. So the geometry it's broken. So like this one and this one, we can see it's not a full circle or ellipse. It's kind of moon. So we saw that maybe it was difficult for the system to detect that some logs didn't have the same geometry. And the next one, the last really important class, because we had really problems with that kind of logs, it's when they are covered by parts of the track. So this breaks for completely the log phase, and that we wanted that the system actually detects them. So we trained YOLO version 3 with images from the best lighting conditions. And we could have really good results. I mean, more than 90% of good detections, but also we detected many problems in other conditions. So for example, in different lighting conditions, we couldn't see what happened. Logmeter had some lights for night, but they were enough to get a good result with our segmentation system. So night was a really problem, but also sunset was really hot, and rainy days, or when it was dark or too illuminated. Another problem was that some tracks had grills which cover the log faces, and it was really hard to detect them. And finally, the rain and fogging, which deform all information that we could get from the image. So in a second stage of the segmentation process, we focused on get a better image. So we made a series of improvements to our setup. The first one was to set the automatic camera parameters. At the beginning, when when a truck enters to the road, we take a picture and we evaluate how the illumination is. I mean, we measure the histogram, we take some statistical metrics in order to set the gain and the time of obturation for the camera. Also, we made a gamma correction, so we could enhance the image. For example, here, also our gamma correction, it's modified by the image features. So for example, in this image from night, we couldn't detect anything, but when we apply the gamma correction, we could enhance the image and detect so much logs, sorry. The best improvement, I think, was getting really good conditions for night. So we first added some lights to the Logmeter portal. So for example, in this image, we just had the lights that Logmeter had initially. Then we added some other lights, like here, and we could see more details. But we detected that when the truck was 2 or more meters from the portal, we couldn't see anything. So we added some lights in the road, not in the portal. We added them 2 meters after the portal. So the sun, where the track, it's really good illuminated, it's more extensive. It is really important because in some cases, we can see the logs really near from the portal, but in other cases, the best image is far. So we need more space where the track could be really being seen by the cameras. Well, another improvement was the installation in the camera boxes of heaters that avoid fogging problems, and also a visor that blocks rain. So we had the problem that sometimes when it was rainy, the water was for hours in our setup. So with our new visor, we can block them. So we started with this kind of training with YOLO B3, which had really bad performance in night, like you can see here. And it was really good for daily image, but it has problem when the logs were blocked, for example. So a first improvement we made in the network was changing the version of YOLO to version 4, which was reported as really good. So with the same training set, we got really good results. So we could detect many logs that before wasn't enabled, but we also had problems in night. So we built another training set really big with images from day, night, sunset, etc. And we made another training. So it is the last training, where, as you can see, all the problems were solved, and the mixing between the setup that we built and this new training made us detect so much logs. Currently, we had really few errors in day and night, and even in rainy conditions. So as you can see, false positives are near to 0, and for the general conditions, the undetected logs are near to 1%, and we can see that in night the error is a little more, but insignificant. So then, once we have this segmentation, we need to detect or select which is the best result. So on real time. So we had the detections, for example, of the first image that maybe had two detections. The next one has more and more, and then the logs start to disappear from the image. So we wanted to detect, for example, the image in the center, and to get that number to show the client that this is the number of logs they have. So for each bundle, we try to detect which is the value of log that it has. So we saw that if we analyze their frames, we see something like this, that at the start, we don't get detections. When the end of the bundle start to being captured, we see that the segmentation results begin to get more and more big until we get our best image, our best result, and then it falls because the cameras begins to capture a part where no faces of the logs are observable. So until we get another bundle, it must be working on real time, and also it have to work for tracks of 2, 3, or 4 bundles that were the options in the plant. So we detected the local maximums to select the final result. So after that, we present to the client the results, showing one image per site with the marks of the results, selecting the best frame where we counted more logs. So let's see how it works. So as I mentioned before, at the beginning, we don't capture any log, and then they start to pass. And when a maximum is detected, we can see that the system reports that a new bundle is detected with the counting results. The total logs are reporting here with the number of bundles. So with these results, really good, we detected some opportunities to make improvements. And one thing we are working on now is that sometimes we can't see all the logs in one side, especially when the bundles are so near. So we are working on matching the detections from one side and the other. So we expect to detect, for example, here that all these logs are the same. So we're working on building this kind of nets in order to detect this net in the other image and see which logs weren't detected in the left one that are present in the second one and get a best result. Another improvement we're working on is the stereo vision. We begin with two images from one side, and we can get the disparity of this image. So we are working on with our images from our setup, and we actually could get results like this, and we'll expect to mix these results with the segmentation to get maybe we could estimate the radius of the detected logs. So conclusion after that is we actually could detect the logs, so we can give the client a counting of them. Also, we detected, we built a really good setup that let us maximize the results for computer vision and also detect the logs in really variable conditions of weather and lightning. Our error right now is really pure, means less than 1%, and we expect to get really good results matching two views or more, and finally get the results that right now we have about stereo visions are, we hope that let us get more information about the logs. So in future, we hope to mix the knowledge and information that we can get from lasers, sensors, with image captures. Thanks.